Hello everyone, it's me Robin Koirala. Today I'm here to present on the topic of design optimization of vertical axis wind turbine using CFD simulation. This is the final presentation for the course ENGI-990B, and the supervisor of the project is Dr. Mohsin Jamil. Now, talking about the introduction, wind power has emerged as a critical player in the field of renewable energy source. It is an environmentally friendly, reliable power source. The two primary variants of wind turbine are known as vertical axis wind turbine and horizontal axis wind turbine. Vertical axis wind turbine offer some noteworthy benefits in specific environments such as cities where noise control is crucial, where the breeze is not particularly strong, where there is evidence of turbulence motion of the wind, and the course of wind is continuously altering. There are specifically two types of vertical axis wind turbine. The one is Darius and another is Sevenius. In this project, we are gonna mostly deal with the Sevenius wind turbine. The figure 1 shows the schematic diagram of Sevenius wind turbine, showing the top view, side view, and 3D view. Now, the objective of the project is to improve a vertical axis wind turbine design by concentrating on the blade geometric arrangement, to use CFD simulation to develop torque and power curves for each blade design, to develop which vertical axis wind turbine design maximizes power production and improve operating efficiency. Now, talking about the methodology of the project, first I did was the literature review and data collection from the various internet sources and journal papers. After that, I did was the model preparation in the CAD software known as SolidWorks. Then after, I inputted the 2D model of the CAD into the Ansys Fluent and did the CFD simulation. After multiple design iteration of the simulation, I finally obtained the results and did the result evaluation. And lastly, I did was discussion and conclusion part of the project. Talking about the geometric selection, in this project I selected 3 different design configuration. As you can see in the figure 3, figure 4 and figure 5 shows the 2 blade, 3 blade and 4 blade design configurations of the Sevenius wind turbine. The white curves in the blades, white curves in the figures are the blade profile of the Sevenius wind turbine. So yeah, for this project, 3 basic blade design configuration are selected and simulation are done to find out which blade configurations optimize the efficiency and like produce the more power, and which how many number of blade is appropriate for a Sevenius wind turbine. Now, talking about the simulation, in the figure 6, the circle represents the area in which the blade of the turbines are inserted. So the remaining rest part of the simulation domain is for to observe the air movement which comes after striking from the blade. Now, figure 7 shows the meshing of 3 different blade configurations, and for the simulation model, the plane of the space is specified as 2D. The simulation considered the wind turbine behavior in 2 dimensions. The simulation utilizes a first order implicit approach for time discretization in order to account for unstable simulations. This decision guarantees a strong portrayal of the aerodynamics of the vertical axis wind turbine that vary with time. The standard Kaplan turbulence model, a popular method for modeling turbulence flow, is used to represent viscous effect. This turbulence model helps forecast the intricate vertical patterns surrounding the turbine blade. Standard wall functions are also incorporated into the wall treatment, which is necessary to simulate the boundary layer around the edge correctly. For the material property, standard air is taken for as a fluid, and for the blade material, aluminum is selected, and the properties of both are shown in the table. Now, talking about the boundary condition, which is one of the most important, major important part of the project, like which governs the simulation and like affects the result. So it is really important to precisely select the boundary conditions, and the selected boundary condition for the project are like using an absolute reference frame. The velocity is calculated at the entry point using the magnitude measurement technique in the usual direction towards the boundary. The velocity intensity is expressed as 3 meters per second multiplied by the equation as shown to provide a dynamic input across time. 0 Pascal is selected as the starting gauge pressure, assuming a turbulence intensity of 5% and turbulence viscosity ratio of 10. Turbulence is established using the intensity and viscosity ratio approach. At the outlet, an absolute reference frame, 0 gauge pressure, and a pressure profile multiplier of 1 are used to establish the backflow circumstances. The technique of intensity and viscosity ratio is used to integrate turbulence, matching the pattern at the intake with a viscosity ratio of 10 and 5% backflow turbulence intensity. The backflow direction is determined as a normal to the boundary. Lastly, a stationary wall with no slip boundary condition is implemented for the wall settings. A roughness factor of 0.5 is used, and the wall roughness is established at 0 meter in height. This boundary condition captures every aspect of the fluid dynamics at operation by defining the parameters controlling the movement, turbulence, and interaction inside the simulated domain. These are the videos of the velocity contours and pressure contours for the case first, which is of two blades at 180 degrees spacing. As you can see in the figure, when the air start hitting the blade, the air creates some wake region after it. So these are the figures of the velocity and pressure contour of the two blade design configuration after the simulation results are converged. So the figure shows that the wake flow across the turbine buckets and the vicinity of the downstream region is less vigorous. In this arrangement, the turbine performance is enhanced with fewer blades because the diverted airflow coming from the upstream blade is more evenly distributed. More torque and produced power are achieved because there is a less interference between the blade in this design. The pressure contour diagram displays a favorable pressure distribution on the convex part of the upstream blade. Similarly, these are the videos of the velocity contour and pressure contour for the case second, which is 3 blade at 120 degree spacing. And these are the velocity and pressure contour of the 3 blade design configurations after the results are converged, and the analysis indicates that in comparison to the 2 blade simulation, the wake flow zone across the turbine buckets become a bit more intense for the 3 blade arrangement. In comparison to all other cases, the diverted airflow coming from the upstream blade is more disturbed in this case, affecting the turbine performance. Additionally, the pressure on the bucket concave section is negative, whereas the convex section of the uppermost blade experiences the most pressure. Finally, these are the videos of the velocity contour and pressure contour of the case third, which is 4 blade at 90 degree spacing. And these are the figures of the velocity and pressure contour of the 4 blade design configurations for case third. And of all the scenarios, the wake flow zone across the turbine buckets and throughout the downstream rotor area is the most intense in this arrangement, and you can see a laminar wake flow region for only the third case. The pressure contour figure shows an increase in undesirable pressure on the upstream bucket convex region. The velocity contour diagram indicates that the air velocity is more significant in the downstream zone, indicating inefficient transmission of air energy to the wind turbine. This is due to the increased blade density, which result in less power generation. These are the power output results, and this graph shows the power versus time graphs. The power generation versus time plot provides valuable information about how various blade design function. When using two blades, there are considerable variation in power production, with the highest figure being 10 watt. This unpredictability is probably caused by the fact that wind interaction with fewer blades are erratic. On the other hand, the three-blade arrangement, which peaks at 2 watt, exhibits a more consistent power output. More even power production is probably the result of more consistent airflow interaction caused by the extra blade. The 4-blade design, however, reports the lower power generation at about 1 watt, suggesting that utilizing more blade could offer complication in terms of effective wind energy absorption. This being said, it is interesting to observe that with the exception of 4-blade arrangement, the power generation exhibits a positive trend with time for rest of the blade design configuration. Now, these are the conclusion of the project. Talking about the blade configuration influence, the 2-blade configuration demonstrated the dynamic power fluctuation reaching intermediate peak of 10 watt. The 3-blade design showcased more stable power output reaching a maximum of 2 watt. The 4-blade configuration yielded the least power, approximately 1 watt, highlighting challenges in efficiency with increased blade. Now, talking about aerodynamic considerations, the wake flow around the downstream rotor and between 4-blade turbine bucket was more intense. Deflected airflow from upstream bucket affected downstream bucket, impacting turbine performance, especially with more blades. Unfavorable pressure on the convex section of the upstream bucket increased with added blades. Now, for the time-dependent power generation except for the 4-blade configuration exhibit an increased trend over time. Ongoing improvement in system stability and performance were observed, indicating the potential for enhanced efficiency. Finally, the implication for the future design and recommendation of the project. Finding offer valuable insight into optimizing blade configuration for efficient wind turbine performance. The blade contributes to guide further future wind turbine designs to maximize power generation while ensuring stability and sustainability. These are the references from where I take the papers and did the literature review. And thank you very much for your time and consideration and listening so carefully. Thank you.